right, I have 11:15. Happy Monday, everybody. Please wind your conversations down, as we have a lot to get through today. We are actually going to start real quick with some background info. We need to do pencil and paper before we get out Tinkercad again. But you are going to need your laptops halfway through lecture, depending on how fast this goes. All right. It's about half the classes last time said you don't know how binary numbers work, so I guess realize this isn't something that has formally been taught as part of a prerequisite class, so we need to understand that going forward. So real quick, forget binary for a second. Just think about regular numbers. Okay, you probably haven't thought about them like this since you were literally in like first grade learning how to count by ones and tens and hundreds, right? If we just take a regular decimal system number, say 317, right? Just making up a number. And remember, literally think back to like, my daughter's in third grade now, so I've like seen this on her homework. You have the ones place, and the tens place, and the hundreds place, right? So each digit of this number represents a power of 10. Okay, that first digit's 10 to the 0, this one's 10 to the 1, that one's 10 squared. So to find the total value of this number, you multiply each digit by its respective power of 10, right? 7 times 1 is 7, 1 times 10 is 10, 3 times 100 is 300, so 300 plus 10 plus 7 is 317, right? Like that seems obvious and stupid now, but basically binary is exactly like this, except it's powers of 2 instead of powers of 10. Okay, so if I write a 3-digit binary number, say 101, this first space represents 2 to the 0, which is 1. The second space represents 2 to the 1, which is 2. This third space represents 2 squared, which is 4. And so 8, 16, 32 can keep going, right? So to calculate the decimal equivalent of this number, again, I multiply. The other difference here is that each digit can only be 0 or 1, right? So here, every digit can be 0 through 9. In binary, each digit can only be 0 or 1. Multiply each one by the respective power of 2. So 1 times 1 is 1. 0 times 2 is 0. 1 times 4 is 4. 4 plus 0 plus 1 is 5. Okay, that's all there is to binary. And the important thing in programming then is if I write x equals 101 in a C program, it assumes I'm using decimal, right? If I put a 0b in front of it, then it knows I'm using binary. So that's how I can tell this is the difference between the binary number 101, which is decimal 5, or just the decimal number 101. Now, in the last class, we were writing out all the ones and zeros in the registers because they kind of correspond to the physical port of pins in the Arduino. But I could also just write x equals 5. And as far as the Arduino is concerned, those two lines of code are equivalent. Okay, there's another number system called hexadecimal that we'll talk about maybe next week sometime, but that's all there is to binary. Okay, so you can do that conversion either way, right? You can have a number in binary and convert it to decimal, or you can start with a number in decimal and go the other way to convert it to binary. Yes?
I don't really understand the last line in our 101 plus 0.
So the question was, I don't understand the last line here. That is multiplying each digit, either 0 or 1, by the respective power of 2 to get this line. So 2 to the 0 is 1, 1 times 1 is 1, 0 times 2 is 0, 1 times 4 is 4, and then you add them to get the total value of the number. Just like we did over here, right? 7 times 1 is 7, 1 times 10 is 10, 3 times 100 is 300, and then add those to get the total value. So it's the exact same system. The difference is that binary is just powers of 2 instead of powers of 10. Okay, congratulations, you know how binary works now. Any other questions on that? Yes?
Sorry, I'm confused by 2, can it be 2 squared plus 4?
No, sorry, so this is just two different ways of writing out the same thing. 2 squared is 4, 2 to the first is 2, and 2 to the 0 is 1, so it's multiplying this top number by either one of those. Sorry. So that's just, you can either write it out, just like here, I could write out 1, 10, 100, or I could write 10 to the 0, 10 to the first, 10 squared. Those are also just two different ways of writing the same thing. They're not multiplying.
Okay.
Okay, sorry if that was confusing. All right. And sorry, I went through that really fast because I want to get to the Tinkercad stuff, but if that's, you're not going to have like homework problems where you have to convert between between decimal and binary, but what we're going to see as we kind of go through more programming stuff, sometimes, even though they're equivalent, working with one number system might be more convenient than the other, just for how you read it as a human. So we'll kind of see that going forward, but again, the important thing to remember when you're programming is don't forget that leading 0B when you want it to be binary. If I forget that, then this is 101. It's not binary 101. Okay, covering that with my hand doesn't really work because the projector just projects onto my hand, but oh, you get what I meant. Okay, other questions on the binary thing? All right. Yes?
Just for going back and double checking the lectures, can you make a note of that 0B on the paper?
Sorry, meaning like, don't forget the 0B?
Yes.
Okay,
Yeah,
sure.
so that when we go back through the notes.
Yeah, just to make
Okay.
sure.
Don't forget leading 0B when you are programming in C and want to represent a binary. You guys are gonna kill my wrist here. There we go. Good? Okay. All right. We are going to switch gears to a circuit topic real quick that we're going to need today when it comes to connecting buttons. So, last time we used Arduino pins as outputs, right? We talked about how the Arduino pin can act like a software-controlled voltage source that I can set to either 5 volts or 0 volts. The Arduino pin can also be an input, so it can act kind of like a voltmeter that can measure an input voltage that is sent to it. Okay, but again, it's digital, so it can only read either high or low. It's not like your multimeter that's going to tell you, oh, this is 2.3 volts. And there are analog pins we're going to talk about later in the semester, but the digital pins can just tell you if it's high or low. Okay, so using, can't remember if I did this before, this little kind of flag symbol for an Arduino pin. I could, for example, connect that to, remember the toggle switch in your kit. The switch that we represented with this symbol with the 3 little terminals where it can kind of rotate between those 2 positions. Right? So if I connect an Arduino pin to a toggle switch like that, that's fine, because I'm only either, that switch can only be in 2 states. I can only either be 5 volts or high, 0 volts or low, not a problem. What if I want to use a button instead of a switch? This is what we're going to do today. So if I connect this one of those little push buttons in your kit, which remember had the symbol like that, right? So when I push the button, the contacts close. Okay, so when I push that button, my input pin is going to be 5 volts. What about when the button isn't pushed? It's just kind of connected to nothing, right? That is a problem because the digital pin wants to read either high or low. It doesn't want any ambiguity about what's in between. So this is called a floating pin because it turns out that these pins are kind of so tiny that they are very susceptible to things like static electricity and electric fields from other nearby pins. So if you have a floating pin like that that is just connected to nothing, then the voltage on it can bounce around and kind of freak out and go between high and low, just depending on kind of electrical noise around the pin. So that is bad. If you want to use a button, you can't just connect the button without something called a pull-down resistor. So we're going to have our Arduino pin. We're going to have a button like that going up to 5 volts. And we're going to have a resistor, usually kind of with a typical value of maybe 10 kilo ohms, like that, down to ground. Okay. First poll everywhere of the day. What is the voltage when the button is not pushed? Okay, I have my Arduino pin as an input. So that is acting like a voltmeter. It's measuring voltage. What is the voltage measured by the input pin when the button is not pushed? And I should clarify, remember how we talked about way back at the beginning of the semester, a practical voltmeter has an ideal voltmeter has infinite resistance, so you assume it draws zero current, right? In reality, a voltmeter has some very, very high resistance and draws a little bit of current, but assume that there is no current in or out of this pin. What is the voltage measured by that pin right there?
My thought was, since it's a
Button is not pushed. Okay, let's give it, we're at 91 replies. I'll give it another 30 seconds. Okay, 15, 10, 5, 4, 3, 2, 1. Deactivates. And, okay, good. 89% of you got that right. The correct answer is 0 volts. So if you got that wrong, remember what we have seen repeatedly. If you remember one thing from this class, we've seen this in like half a dozen different examples. If the current into that pin is 0, right? I equals 0. Okay, well this switch is open. So I know the current that way has to be 0, right? No current can go through an open switch. And, okay, that just means the current through the resistor is also 0. Okay, so I just have no current flowing anywhere in that junction. If this end of the resistor is tied to ground, 0 volts. Again, as we've seen over and over again, kind of a boring applications of Ohm's law, right? If the current through this resistor is 0, the voltage drop over this resistor is 0. So if the voltage there is 0, the voltage there is also 0. Great. That's why it's called a pull-down resistor. It is pulling this voltage down to 0 when the button is not pressed, as opposed to up here, where my pin was just connected to nothing and it could be floating when the button isn't pressed. So think of this kind of like a electrical anchor, right, that's holding the voltage on that button in place, okay? But then when I push the button, okay, now the button is pressed, and that is the next quick poll here. What is the voltage when the button is pushed? Okay, so I still have my 10 kiloohms. I still have this acting as an input. But now I have an ideal 0 resistance switch. Or sorry, ideal 0 resistance button. Going directly from the input to 5 volts. So what's the voltage on the input when the button is pushed and held down? Okay, we're going to do this one pretty quick. I'll give it another 20 seconds. All right, 5, 4, 3, 2, 1. Deactivates. Okay, about 76% of you got that right. So a lot of you said 2.5 volts, about 20%, and that is kind of an incorrect application of the voltage divider concept, right? If this was also a 10 kilo ohm resistor, then you would be right. Then I would have a voltage divider cutting this 5 volts in half to 2.5 volts, right? This is an ideal zero resistance. So just treat it like a wire, right? So the input is connected directly to 5 volts. So the input voltage measured here is just also going to be 5 volts. Okay. Another way to think about it is if you wrote out the voltage divider equation where R1 is 0, then the fraction in the, I'm not going to take time to write it down now, but then the fraction in the voltage divider equation is just going to be 1, right? So it's the output equals 1 times the input. So we do have some current flowing here, right? So the current is no longer 0. This is why you want to use a big resistor for your pull-down resistor, because you don't want to waste a lot of current flowing through the button when you're just holding the button down. We have some current flowing, but there's no voltage drop over this ideal zero resistance button. In reality, does that button have a few milliohms of resistance, and is there a tiny little voltage drop over it or something? Yes, but what I didn't mention is that when we talk about logic levels, I kind of lied before when I said the Arduino can only measure either 0 or 5 volts. There's sort of a range where I don't remember, I'd have to look this up off the top of my head. I think it actually considers anything above about 3.3 as high, and maybe anything below about 1.8 as low, where that in-between range is going to be floating. So even if there's a little bit of voltage drop across this switch because it has some finite resistance, and this is 4.99 volts instead of exactly 5 or something, that's fine. The Arduino is kind of going to think of it as either rounding up or rounding down, right? As long as you're close enough to 5 or 0, it's going to consider that either high or low. Okay. Questions on the pull-down resistor thing? Again, button not pushed. This just makes sure my input is 0. Button pushed. This makes sure my input is 5. So I'm only in between one of those two states when I push or release the button. Yes?
So is the correct logic basically to choose the, how big the resistor be as large as possible to minimize the current?
The question was, should it be as large as possible to minimize the current? Sort of, but only to a point, because remember that we're kind of treating this as an ideal infinite resistance, zero capacitance thing right now. There's also a little bit of capacitance on the input pin. So if you make this resistor huge in like mega ohms or tens of mega ohms, then you'll actually see kind of a bit of an RC time constant because it takes a second for this to charge up. So 10 kilo ohms is kind of like a standard rule of thumb value. I think for the speeds we're worried about in this class, hundreds of kilo ohms or even mega ohms probably wouldn't hurt. But if you hooked an oscilloscope up to this pin and zoomed in really far with different resistance values, you would actually kind of see, just like, I don't have the slide pulled up, but last time when we looked at toggling, the slide where I showed toggling the Arduino pin with the Arduino functions versus the registers, right, where we could actually see the RC time constant on the pin charging up, right? So adding a big resistance effectively increases that time constant. So usually from what I've seen, you can do the math, but 10 kilo ohms with a 5 volt source still gets you a really, really small current, so you're not wasting a ton of power in the resistor. Okay. Now you can, I messed up my spacing on the paper here. You can flip that if you want and do a pull-up resistor that basically inverts the logic. So rather than having the button connected to 5 volts, you have the resistor connected to 5 volts and the button connected to ground. And that will give you 5 volts when the button is not pushed and 0 volts when the button is pushed. And that just kind of, so the functionality will be exactly the same. It just depends on which one is maybe more intuitive or how you want your code to work. Because you can still go code an if statement, sorry, something stuck in my tooth, to do something depending on whether the button is pushed or not pushed in either case. And so if you hear the phrase pull-up resistor, functionality is conceptually identical to a pull-down resistor. It's just reversing the resistor in the button. Okay? Questions on either pull up or pull down resistors, because we are going to need these today when we are connecting buttons. Yes?
When would you choose, like, if you're just using your like microcontroller to register whether this button is pushed or not, when would you choose to pull up or pull down? Or just like either way you'd be able to recognize if the button is pushed.
Honestly, it's just whichever one is more intuitive for you. I kind of like, for me, this is more intuitive because it also, I guess, depends on the default state of the button. So like when the button is not pushed, I think of that as off, right? So 0 volts corresponds to off in my head. And then when I push the button, I want something to turn on. So when you push the button, the input goes high. So if that is more intuitive to you, like I push the button to turn something on, then you would choose this. You could still do that here, it's just the logic would be reversed in your code. When you push the button, the input goes low. Maybe this would be more intuitive for something where like the button is something like a safety interlock on a door for a laser cutter, right? So, or like the lights that turn on when you open the doors to a refrigerator, right? There is a little switch in there that is normally closed. It is pressed closed by the door being held shut, and then when you open the door, the switch opens. So like the lights turn on when the switch is open. So like maybe this could be more intuitive in that case, but otherwise it's kind of a coin toss. Okay. And we're going to talk more about, we're not going to get to it today. There is also actually an internal pull-up resistor in some microcontrollers. So rather than having to connect, today we're going to wire an external one on the breadboard. Some microcontrollers, including the Arduino, have an internal one that you can turn on with code, so you don't have to wire an external one. But the Arduino only has an internal pull-up. It does not have a pull-down option. So if you want to use the internal one to save cost on your breadboard or whatever, then in that case you have to use the internal pull-up. But we're not going to get to that today. Okay. Other questions on pull-up and pull-down resistors? All right. Then what I want to do is switch over to Tinkercad. So get up. And you could start by, plug the HDMI cable in. Making a copy of one of your circuits from last time. You only need one LED for now. So depending on how many LEDs you added last time, or like if you have an earlier version of the circuit that only had one LED. Okay, you only need one LED, I used pin 7 last time, so you should ideally already have a circuit that has an LED on a different pin. I want you to do the same thing with the button. I am using pin 8, use a different pin for your button. And look at how this button is wired. Remember we did this back in lab 2 and with Tinkercad earlier in the semester. Rotate it so it straddles the gap in the middle of the breadboard. You're going to connect one end, I have the top here, to 5 volts. And then the other end gets 2 connections. There's a 10 kilo ohm pull down resistor to ground and a wire to one of the Arduino pins. Okay, so this is, I can't really show both at once here. This is the equivalent of the circuit diagram I just do with the pull down resistor, right? So I have the top and bottom of the button. Top of the button goes to 5 volts. Bottom of the button goes to ground with a pull down resistor. And then that goes to the Arduino pin. So when I press this button, this row is just going to be shorted to 5 volts through the button, so that's going to pull the input high. When the button is not pressed, this part is open, so the input is pulled down to ground through the pull-down resistor. Okay? So wire the button up, and then we are going to look at the code to turn the LED on using the button instead of just flashing the LED kind of in a hard-coded manner. And again, motivation being we are using simple hardware, buttons and LEDs, so you can focus on the programming part. For your robot, you are going to have motors reacting to sensors. Okay, so you're going to have different inputs, and your output is going to be controlling your H-bridge, which is going to be controlling the motor. And we'll get to the sensors starting kind of next week. Okay, we'll give it like another minute just for people to get the button wired up, and then we are going to look at the code. I'm going to move this over here and give myself a lot of room for the code. Bigger. Okay, I already have the font as large as it can go. All right, main function. Same as last time. Okay, I'm setting my LED pin as an output. I just have my data direction register with a 1 in there. Something that came up with a few questions after lecture last time. When people were adding a second LED, they came up and said, okay, I have code like, say I also wanted to light up an LED on pin 6 or bit 6. I'm doing that. Why isn't my first LED working anymore? That's because your second line here is overwriting the first line. Okay, so this 0 is just overwriting that one. And we are going to talk more, depending on how far we get today and Wednesday, about how you can set individual bits without overwriting the other bits. Yes?
Did you mention the resistor values that you're using?
10, the question was about the resistor values, 10 kilo ohms for the pull down. And in Tinkercad, it doesn't matter since you're not really dissipating real power. 220 for the LED, which again, if you make that too small, Tinkercad will do a little explosion animation, but not critical in Tinkercad. It matters more in real life.
And then where's the green wire going?
Green wire is going over to an Arduino input pin of your choice, but don't use pin 8, because I want you to have to work through this yourself and not just copy what I'm doing.
Okay, so it doesn't, we will set the pins as input or output, right?
Yes.
Okay.
Okay? So, all right, now, the pins all default to inputs. So I have my button on port B, bit 0, which technically defaults to an input. So if I want to write this out to make myself feel better and remind myself that, oh, I set that as an input, I can. Technically, I don't need to do that because they all default to inputs, okay? So if, for example, you have your button also on the same port as your LED, you wouldn't need this DDR-B line. You would only need the DDR-D line, and then whichever pin your button is connected to is just going to be a 0 anyway. Okay? So as you add more and more things for your robot, again, it might help to do that just to be 100% sure that the pins you think are inputs are set as inputs. Technically, you don't need to do it. Okay. We're going to initialize serial communication again. So serial.begin 9600. We're going to use this to print out messages. And then in our while loop, we're going to have an if-else statement. So don't worry about the condition in the if statement yet. I'm going to go through that in a minute. But the syntax for an if-else statement in C is if regular parentheses for your condition, which looks kind of weird. We'll explain that in a minute. Open curly bracket. Okay, and then whatever code is going to go inside your if statement, if this is true, close curly bracket, else, and then another open and close curly bracket. Okay, so don't worry about filling in the if statement yet, because we actually need to switch over to PowerPoint for a second to explain this, and then we're going to come back to the code. Okay, so just kind of get it set up so you have everything there with your if statement ready to go. Again, I'll give that. So basically, don't worry about this yet. Don't worry about this yet. And don't worry about the actual condition for the if statement. Yes?
Sorry, I don't know if this is part of the thing we're not supposed to worry about. What is PB?
Sorry, what is pin B?
Yeah.
Don't worry about that yet.
Okay. Just write it regardless of ones we
No, don't even fill that in yet. Don't copy that because that's going to be different depending on which pin you pick for your button. Okay, I still hear lots of typing, so we'll wait another couple minutes here. And don't even, so sorry, by don't worry about this, I meant don't, just leave that blank for now. Okay, because this line, the port lines here are going to be different depending on which pin you have your LED on, and this pin thing is going to be different depending on which pin you have your button on. Okay? And so you should have, again, assuming you copied your program from last time, you should have kind of had the skeleton of the code here already with the main function and the while loops. Remember, this is code that only runs once, or setup stuff at the beginning, and then code that loops forever. All right. I want to make sure we have enough time to get through this today, so I'm going to switch over to PowerPoint and then come back here. So if you're still typing, you'll get another chance. But we need to kind of explain. Okay, we talked about data direction, right? How do we set a pin as an input or output? And we talked about how to set an output pin high or low. We haven't talked about how to read the value of an input pin yet. So that's what we need to do now. How do we know? How does our code know if this button is pushed or not? To do that, we are going to switch over to PowerPoint. And I forgot to get my little remote clicky thing out so I can walk around. Bear with me. All right. We need to introduce concepts called bitwise operators and masking. All right. Problem. I want to control two LEDs independently. So we saw this with the issue with overwriting the registers, right? Like if I set these pins as outputs, fine. So I set both pins as outputs. And then I turn pin 7 on. So the port D register turns pin 7 on. But say I want to leave pin 7 on and I want to have pin 6 kind of react independently to a button or some other input. If I do this, if I turn pin 6 on, then fine, this turns pin 6 on, but this 0 overwrote that 1. So I have now accidentally turned pin 7 off, and I would like to be able to control them independently without always turning one off when I try to turn the other one on. Okay? To do that, we need to learn about something called bitwise operators. So you should know from a previous programming class the basics of logical or, and not, right? Either from MATLAB or Python, right? You can have an if statement where if this is true and this is true, then do whatever, okay? So I'm not going to teach you what and or are, but we are going to look at it with ones and zeros. So if I just take 1 and 1, right, or true and true equals true, right, just in Boolean. This will, where we're going with this will make sense when we kind of circle back to the register stuff. 0 and 1 is 0. False and true is false, right? For and to be true, both things have to be true. Okay? 1 and 0 is 0. 0 and 0 is 0. So you might also hear this referred to as a truth table, right? For logical operators where you have the two inputs and then what the output equals. If I look at this with individual bits, if I AND something with 1, then the first bit doesn't change, right? So if the first bit here is kind of my input and then I AND it with an operator, then it doesn't change the first bit if I AND it with 1. If I AND something with 0, then the first bit is set to 0 or clear, right? The output is always 0 here regardless of what the input bit was, okay? So this is a bitwise AND operator acting on individual bits. We can do the same thing for OR. Okay, 1 or 1 is 1. I'm going to go through this a little faster. 0 or 1 is 1. 1 or 0 is 1. 0 or 0 is 0. So there, if I ORed something with 1, the output is always 1. If I OR something with 0, then the result is unchanged. Okay, 1 is still 1 and 0 is still 0. Okay? I can also do exclusive OR or XOR. So if you haven't seen that one before, that is only true if either one of the inputs is 1. It's not true if both inputs are 1. So it's different from regular OR. So I don't have this one animated, but the XOR operator in C is the up caret thingy. So 1 XOR 1 is 0. I'm not going to read all of these, but it toggles the input bit, right? So if I XOR it with 1, the input is the opposite. Sorry, the output is the opposite of what the input was, and if I XOR it with 0, the output is unchanged. Okay, I went through that really fast. This is going to be in the reference slides. I want to try and get through why we would need to know this. Okay, this is also going to be in the reference slides. There's still a little summary table, so those last 3 slides break down all the examples, but this says, okay, if I AND something with 1, it leaves it unchanged. If I AND something with 0, it sets it to 0, and so on. I realize I'm going through this quickly, but I want to get back to the Tinkercad stuff, so this will all make sense, hopefully, in a second. Okay. So, again, we have this. We already set bit 7 high, and our goal is to make bit 6 high without affecting the other bits. So even pretend I had all 8 LEDs hooked up, right? And I just want to control one of them without changing the state of the other 7. Okay? That is bad because it's overwriting all the other bits with zeros. So I can use a technique called masking, where I do a bitwise operation on the individual bits in the register. So this is a little easier to see in kind of vertical format like this. So imagine this is my original value stored in port D. Okay. This vertical bar means a bitwise OR operator. So it's not doing OR on the entire value, it's doing a bitwise OR on each individual bit. Okay, so I can go vertically here. 1 or 0 is 1. 0 or 1 is 1. And then for all the rest of these, 0 or 0 is still 0. Okay, so look at my resulting output. I successfully set bit high, but I didn't set bit 6 high, but I didn't change any of the other bits. Okay, this is where we were going with all the previous 3 slides. Again, I'm going to go through that again one more time to hopefully make this clear, and then we'll do questions. Here's my current state, right? I have LED number 7 high. I want to turn LED 6 high without affecting LED 7. So if I just write this, that's bad, because I overwrite LED 7. If I do a bitwise OR operation on every single one of these bits, then on that 1 here, remember if I go back to this table, if I OR something with 1, I set it to 1. If I OR something with 0, I leave it unchanged. So in my bitwise OR operation here, the only one I set to 1 was the one I wanted to change to 1. I left all the other ones as 0, so it left their original value unchanged. Does that make any sense at all? I see some nodding. Okay. Questions? 0 questions. You all believe me? Yes?
Can you go back one slide?
Yes.
So, does it matter if you do a 0 first or a 1 first? If there's a 1, the 1 will carry in. But if there's a 0, it won't.
Where, so if you do a 0 first row, I don't totally, you mean,
Like the vibe I got was that if there's a 1, things will change. If there's a 0, things will not change.
it depends on whether you're doing and or, right? So if there's a 1, yes, so for or, what you just said is true, right? If there's a 1, it'll change it to 1 if it was a 0. If it's a ORed with a 0, it'll leave it unchanged. Okay? Okay, and then that's kind of, so each one of these operators has different behavior as described by the row in this table. Okay? So basically, I forget if I have a second example here. Perfect, I have a second example. Okay. So, say now, great, both of those are on, but I want to turn bit 7 off without affecting the other bits. Okay, I want to leave bit 6 on. And if I just do that, again, that's bad because that's just turning everything off. Okay? So now I can use the bitwise AND operator, where I'm not going to keep clicking back and forth through the slides, but if I AND with 0, it's going to set it to 0, and if I AND with 1, it's going to leave it unchanged. So here's my original value stored in port D. I AND it with this, so I only want to set bit 7 low. I AND everything else with 1, and that leaves this part of it unchanged, right? Bit 6 is still high. The others are all still 0. So I just want to turn one thing off without turning everything else off. I use the AND operator instead of the OR operator. Okay? No. Yes? Sorry, behind you first and then up here.
Is there a reason that you filled, I guess, 6 through 0 with 1s instead of 0s?
Yes, so if we go back to this table, because with the AND operator, if I want to leave something unchanged, I need to AND it with 1. So the behavior is different than the OR operator. Okay, so if these were all 1s, it's leaving these 0s unchanged, so in that case it wouldn't matter. But if I ANDed this, or, sorry, I got that wrong. No, sorry, I'm on the wrong slide, that's why. Okay. Here, you asked why I filled these with 1s instead of 0s, right? So if these were 0s, 0 and 0 is still 0, so it wouldn't matter, right? But if, it's 7, if this was a 0, right, then I would be turning bit 6 off, and that's not what I wanted to do, right? So when you want to leave something unchanged, you AND it with 0.
But for 1 through 6, doesn't matter if we filled out with 1s or 0s?
In this, say that the state of these other ones was unknown. So I'm giving an example where those were all 0 to begin with, but say I filled each of these in with a question mark. right? I just had 6 LEDs being controlled by other buttons, and I didn't know what their state was, then if you don't want to affect them, you need to AND it with 1. Okay, and in this specific example, you're right, where I said these are already 0, then if I ANDed at 0, it wouldn't change the output, but assume I have 8 LEDs being controlled by 8 different buttons, and I only want to turn 1 off. Okay? All right, question?
Sorry, so would this work in the same way with bit shifting, if you're using that for the 2 definition?
Yeah, so the question was, would this also work with bit shifting? Yes, but I don't have examples using it with bit shifting in these slides. I would have to sit down and work out how you do it, but you should be able to do, so I'm terrible with bit shifting, so I know the answer is yes, but I don't have it off the top of my head. All right. So finally, at the very, very bottom here, I don't know if you can see this in the back, I missed this on the previous slide, there's a shorthand notation for this. So rather than writing port D equals port D or whatever, you can just do port D or equals, okay? And that's gonna set, it's the same as doing this, it just saves you from writing out the second port D. All right. I'm gonna try and get to this in the last 5 minutes. All right. That was all set up for circling back to what we're doing in Tinkercad. How do we read an input pin? Okay. So in the Arduino language, there's a command just called digital read, right, that tells you whether a pin is high or low. In registers, there is something called, so this is what you asked 20 minutes ago, the pin register. Rather than setting the output value of the bits like the port register does, it stores the value of each pin, whether it's high or low. Okay. So it always does this for all 8 pins in a port, even if they're set as outputs, right? So if you have an LED on, the corresponding bit in the pin register is also going to be high. Okay? So for example, if pin 3 is high, PD3, and all the other pins are low, then the value in PD will be, and I realize this kind of gets small and low down here, 0B, 0, 0, 0, 0, 1 for pin 3, 0, 0. Okay, so it is storing the high or low values of each pin. And, okay, great. How do I know if that is high? I'm going to use that in the condition for my if statement. Okay, find out, is the pin on this button, is the pin this button is connected to high? Your first instinct might just be to write, okay, what if pin D equals 0B with a 1 wherever I have my button connected, right? And side note, in C, the double, I don't remember what this is in MATLAB or Python at this point, the comparison equal operator is double equal sign, not single. Single equal is the assignment operator for like x equals 2. Comparison operator is double equal. That only works if my button is the only thing on that port. Okay, if I have other LEDs or buttons or things on that port, then that is only going to evaluate true if pin D is exactly this. Say I have some other button on a different pin that is also high, then this condition will be false. Right? So that fails at detecting just this button press. We can detect just that button press using bitwise operators and masking. Okay? So sorry, those bullet points are just saying everything I just said there. All right, we only want to check if this bit is high or low, and we don't care about the other bits. So we do that. Basically, we don't care what these other bits are. These are question marks. We just want to know if x is 1 or 0. Okay? If we take something with a bunch of unknowns and do a bitwise AND with zeros and a 1 on the bit we want to check, then the output is going to be just all zeros with whatever the value of x is here, right? Whether x is 1 or 0, okay? Because I'm ANDing all of these with 0, the output for those is going to be 0 regardless of whether this is a 1 or a 0, okay? So the result is just going to be a bunch of zeros with x, my original unknown bit there. C treats any non-zero number as true, right? So even though the equivalent decimal value of this binary number is going to be, whatever, 2 to the 0, 2 to the 1, 2 cubed, or whatever it is that is 1, C still treats that as true. Again, I don't remember how MATLAB or Python do that, but 0 is false, 1 is true, 10 is true, 100 is true. Okay? Any non-zero binary number is going to be true. Okay? As always, it's false, x is false. Sorry. So finally, To check if pin 3, bit 3 of port D is high, we use this. If pin D, bitwise and 0B, 8 zeros with a 1 filled in for the pin, only the pin we want to check, okay? That was like a 15-minute explanation to circle back to what do you fill in for that if statement to detect if your button is pushed? This. Pin, either B or D, depending on which port you put your button on, and then the register, and again, this is where you could use bit shifting if you didn't want to write it out like this, and with a 1 for the pin you want to check for your button. So, I'm going to go back to Tinkercad. That is what goes, and I think we should have enough time to do this. Fill in this condition, okay? Depending on which port you put your button on, this is going to be either pin D for down here, pin B for up here, bitwise and, okay? Do not do a double equal sign, or that condition might not always be true depending on what other buttons and LEDs you have connected. In this specific circuit, where I only have the button on pin port B and nothing else, that would actually work. Okay, but if I add another LED up here or another button up here, any other stuff on port B is going to mess that up. So do not do a double equal. Do the bitwise and. Just write out 8 zeros by default, and then change the bit or pin your button is connected to a 1. Okay, and then once you have done that, you can fill in the rest of the if-else conditions, where for me, if the button is pushed, I'm going to turn my LED on, so this should be the same from what you had last time with the port register, and I also have the serial print command in there for debugging purposes, and then in my else, I'm turning my LED off. Although, what I should be doing there is actually using masking to set my LED on. So remember, if I have a problem here, if I had my button also on port D, and say, so I press my button, my pin on port D goes high, but then I immediately try to overwrite all of port D and set it low, that's going to mess up my input. So for controlling the LED, and you're going to want to do the same thing when you're using your motors, you actually also want to use masking to control your LED. And I can change this to do the same thing down here, where I'm going to do bitwise and 1, 2, 3, 4, 5, 6, 7. So this is now only setting pin 7 low without affecting the other pins. So if I had other LEDs, other buttons, or anything on port D, this now only turns pin 7 off. So I'll change the comment here without changing other pins. And set pin 7 low without changing other pins. So I realize that was kind of fast today, but I wanted to get to this in time for you to have it for the first part of homework 6. On Wednesday, we are going to talk about interrupts. So basically how, if you have delays or parts of your code that are taking a long time to run, how do you detect a button press without missing it? If you want to work ahead on homework 6, there are videos walking through interrupts linked in the Tinkercad playlist at the bottom of Canvas, but we will do that in a lecture on Wednesday. Okay, and I'll stick around and leave this up if you're still typing and want to catch the rest of it. All right, thank you.